Okay, questions from the homework? Gotcha.
Number 41.
Homework number 41 on homework number 9. Does anybody know what that is?
Oh, I can tell you.
Thank you.
I just wrote it. You want to look at it?
Do I need to?
I just wrote
I don't know. I need to get it.
Couple of times.
Oh, yeah. So, 41, we have a circle with a radius 1 unit is riding along the x-axis. They kind of give us a funky little picture there. We start with this thing, and then we're going to see it rolls along there, and it's going to kind of trace out a path that looks something like that. And so, let's see, at t equals 0, p is at the origin. So our point is going to start right here at the origin at time 0. And the path of this thing is actually called a cycloid. And we did this in the other class. We can actually graph this on your calculator. It's kind of funky looking. Anyway, we'll refer to the diagram at right above. And then we also are given, so as an aside, they are giving us a circle. And that is supposed to be telling us that, let's see, they call this point A, and the center they're calling C.
Where did the other letter came from?
What's that?
Oh, nothing.
And this is going to be relevant, isn't it? Or is it? So we're going to need this, I think. So there's our point xy. And then we're going to draw our right triangle there. And this distance along here is t. And so that's going to tell us, since it's a radius of 1, that I'm calling this our angle theta. Right? No, that's going to be, we're going to go radian, so that's our angle t. So there's our angle, right? And so this side length is going to be, for this angle, is adjacent over hypotenuse. So this side is going to be the cosine of t, and this side is going to be the sine of t, I believe. Are we okay so far? And okay, so part A, refer to the diagram at right and above and explain why at time t that OA is equal to t. OA is equal to t. Where is O? O is over here. This is O. And so OA is this distance right here. And why is that equal to t? So if you can see here, so what we're doing, if you start, here's our circle in its starting position. And then as it rolls this way here, then the distance it travels along here is going to be this distance that we travel along there. That's what the kind of the rubber meets the road, where that tire's touching it. So this distance that's gone here, this way for t, is going to be that distance where we started. So that's going to be the same as that distance there. Like if you backed it back up, you would come right back to where we started. Does that make sense or no?
Kind of.
Gotcha, that doesn't look like a tendency. Yes. Let's see if I can explain this. So here's our circle. My fingers are the circle. Okay, so now we're going to go along. Here's going to be our angle t. As this thing rolls along, then when we stop there, this angle t is going to be the same as that distance we traveled. Is that okay? Okay. So that was our first challenge. OA is equal to T and arc AP is equal to T. So because we're radius 1, then the arc length and the angle are the same. The angle in radians is the same as the arc length. So that's trying to convince you that OA is T, and also that this arc length AP is T, and therefore the measure of this angle is T radians. Okay? Good to go. I need nods of heads. Karen, you okay?
Yeah,
Can we go through it again there?
if you don't mind reading all of
No, I don't. So we're imagining like this thing, this is like a wheel rolling. So here's our wheel, and we're starting right there. Now, imagine we just ran through some paint along here. So now as this thing rolls, it's going to leave some paint along here. Now, the paint is coming from, as this thing rolls, the paint is going to come from this part of the wheel that's making this path. Now, keep your eye on that over here. This is that part of the wheel. If we back it back up, this is going to come right back to where we started. So the part that's generating this much, it doesn't look to scale here, but this distance is the same as that length there. Now, once we get that arc length and that distance are the same, then for an angle with radius 1, the arc length is the same as the angle in radians. And so now we've got equality through all that. This, that arc length, that angle, all are T. And then as this continues to roll, we'll go further along here, and this arc will extend further around the circle there. Okay? Okay, so that was part A. Part B gets a little even more challenging. So use the fact that OP, so vector OP is equal to vector OA plus vector AC plus vector CP to show that, oh goodness, that XY, we're going to try to convince you of, is equal to T minus sine T, comma, 1 minus cosine T. And then from there we can get the parametric equations. This is going to be the challenge. All right, here we go. So vector OP is going to be this vector right there. And the claim is that's going to be AC plus CP. Don't like my picture. Is that the way it looks?
OA plus AC plus CP.
OA plus AC. Okay, so this is our OP. So we're going to go OA. So we're going to go, I don't have the colors. So we're going to go OA plus AC plus CP. Is that okay? Now visually, that's what we talked about, how we add vectors. So we go tip to tail. So it's like you're going from, you start here, you go to here, then you turn and go here, there. So that's what this is saying, which visually is correct. It agrees with what we have there. Okay, now, how can we show that that's going to lead to this? So let's see. What does OA look like? OA is going to look like this right here. So it's everything going this direction. We said that's T right there in the X. And we're not going up and down at all. So it's going to be 0 in the Y. So this OA is going to be T comma 0. We're going to add these vectors. We're going to figure out what these vectors are and then add them together. And if all goes according to plan, that's where we're going to end up. Okay? So AC. Now AC goes straight vertical. So it's going to be 0 in the horizontal. And it's going to be this distance, which is a radius, which is 1. So that's going to be a plus 0, 1. You okay so far? Yeah. Now let's see, CP. This is going to be more challenging. CP, we're coming down this way here. So we need an X component and a Y component. Now the x component they're trying to tell us is the sine of t. Now t looks to me to be an acute angle, right? But since we're going left, that should really be negative. Since sine of t looks like it's going to be positive because it's in quadrant 1, it's an acute angle, we're going to have to oppose the negative and call it a negative sine of t. Want to run that by again? So, we're saying that t is this angle here because of the arc length, and that's what the angle is in radians. You can also see it visually as this angle right here. Now, I see that as being an angle that is less than 90 degrees. Okay? So that means that its value, the sine of that angle, is a quadrant 1 angle, is going to be positive. But this vector, I can see, this vector right here is going down and left. So its x component should be negative. But the sine of t, which is a quadrant 1 angle, is going to be positive. So I'm going to impose the negative sign to make that be a negative horizontal component. So it really is going left. Okay? In a similar fashion, this distance here, that vertical component, we're told that we can see as the cosine of t. But again, this is a quadrant 1 angle, that's positive, but it's going left, which means it should be a negative. So I'm going to impose that as a negative cosine of t. Are we okay? Okay, so let's see, do I have everything? Boom, boom, boom. Now I just get to do the arithmetic. So adding the x components, we have t plus 0 plus a negative sine t is going to be t minus sine t. Adding the y components, we have 0 plus 1 and a negative cosine t. I love it when it works out like that, just like it was supposed to.
So how do we know that OP is equal to those three added up? Was that just like given to us?
Well, they gave us that hint, but we can do that at any point in time. And you know the next one, so you're good to go. So in general, we can do that any way we want. I mean, you know, the way we add vectors is we go tip to tail. And so that's good. That geometrically represents addition. Well, that means if you start with this vector and you want to say, well, what adds to be that? You've got a lot of leeway. You can make a path.
Okay. Sorry.
Wow, we missed you. Nice to see you back. What happened?
It's canceled, it's raining.
Oh, you don't go there and then they tell you it's canceled?
You can't play in the rain?
Came here, and now we get to it.
You got that right there. I got that one.
Oh, that'd be pretty
Wait
unfortunate.
till they stop free rides on the way.
Well, the poor
Oh.
bus.
Yeah.
Oh, yeah. Is that okay?
Can't play in
Yeah.
the rain, that's the way.
Where's the toughness? Is that okay, Macy?
Yeah.
So you could, and then so this plus this plus this plus this plus this has to be that vector.
Right, but in the picture, it doesn't really look like that.
Yeah, well, that's, and it kind of looks bad because these, in my picture, look like they're collinear, like on the same line. But let's just, and this isn't really drawn very well to scale, because that would, I think, throw Karen when I was trying to say that all of this is equal to that. It doesn't look right. Okay, but that's my drawing issue, not that, because
Okay.
it might be better shown here if you look at, like, you know, this might look better where this is going to be the same as that. Something like that, if I get it right. So what I'm trying to do is, if I back this back up, if I go backwards in time, this point is going to match that point, is what I'm trying to do, but obviously not doing very well. And so even though I stopped it here, which is not a great place to stop it, you know, it might be even better if this went like this, and then you have the vector going there. And so you're still saying that to go from here to there, we can go here, this, plus that, plus that.
Okay,
So,
Yeah.
so the way to look at it is this, you're adding these vectors and kind of walking the path on those
I
vectors
see
to get there.
okay.
Yeah, my picture is not helping us at all. All right, other questions? Does that help, Macy, Carlson? Okay, we're good to go there. Karen, we all right with that? Grace?
Like, at least be part of 27.
I don't know, 27?
Yeah. I'm so much tired.
So 27, before graphing, describe what you think the curve with parametric equations x equals 2 cosine t. Am I on the right problem?
Yeah.
And y equals 5 sine t looks like. Unless you've done this a few times, that might be a tough question. Then graph the equations. So that's part A. Did you want to do that, or?
Yeah, that's fine.
Okay. And then we're going to find the Cartesian equation. That means eliminate the parameter. So we want to change them to rectangular. So Cartesian and rectangular are synonyms. Find the Cartesian equation. And then after we do all this, we're going to say, how do you suppose this ellipse is related? Okay, so, and I don't know how you would really be able to answer part A very well until you've done a few of these, which you have. So that's going to be pretty challenging. So I'm not really too worried about that yet. But let's see, to find the Cartesian equations, we have to do what's called eliminating the parameter. So we want to get rid of the t's altogether. And we had, if you saw I don't know if the lecture was on there from yesterday, there's two strategies depending on if you have sines and cosines or you don't have sines and cosines. These do have sines and cosines, which means we're going to tap into our most famous of all trig identities, sine squared plus cosine squared equals 1. So instead of trying to get the t completely by itself, which would be messy, because you'd have to do an inverse sine at some point, we're just going to get the sine of t by itself and the cosine of t by itself. So here, that's going to give us cosine of t is x over 2, and here, we're going to get sine of t is y over 5. Is that okay? Now, we're going to substitute those in for the sines and the cosines. And I like to write the x's first. So I'm going to, even though this is the cosine now, I'm going to go x over 2 squared plus y over 5 squared is equal to 1. Okay? So now we've done it, although it's not very recognizable yet unless you really, really know what you're doing. So I would multiply them out, square top and square bottom. So x squared over 4 plus y squared over 25 is equal to 1. Now, this may or may not ring a bell, because it was a long time ago, and we didn't do it for very much. It was like just in a blink of an eye. Do you remember what this is supposed to be?
Well, based on the answer.
Based on the answer, but not based on any memory that you have.
Correct.
This is actually an ellipse. So if these numbers were the same, we could, like if this was also a 4, we could multiply through by 4, and we get x squared plus y squared equals 4. That you would recognize, circle, centered at the origin, radius 4. When these are different, that means we have different radii. So it's going to become an ellipse. So that, if you imagine starting with a circle centered at the origin, radius 1, then you're going to stretch it in the x direction 2, because the 4 is 2 squared. So it's going to have a radius of 2 in the x direction and a radius of 5 in the y direction. So you're getting this ellipse that looks kind of like this. And because we don't have any x plus or minus h squared or y plus or minus k squared, it's going to be centered at the origin. And so this radius is going to be 2, and this radius is going to be 5. And that's known as an ellipse. Okay. So, if these numbers had been the same, we would have gotten a circle. When they're different, you're gonna get an ellipse. And then if you have different trig functions, then it may not be the Pythagorean identity here, but it might be the one with secants and tangents or cosecants and cotangents. And so you may get, instead of an ellipse, you might get like a hyperbola or something like that. We're not gonna make a big deal of that, but just for the record. So here's the Cartesian equation here. We've done part B. And now how does that compare to this thing? Well, I'm betting,
Well, they're both ellipses.
they're both ellipses. I was gonna say, we multiply through by 100, I was hoping they'd be the same. But here, but I don't think that's gonna happen. 25x squared, this would cancel, be 4y squared equals 100, so that's not quite the same ellipse. But this is gonna be another ellipse, we're close. Not quite. Okay? I don't know what they're looking for on that one. What was that question? For 27, part C. Ellipse that's, what do you think the parametric, oh, we can do that. So without doing a lot of work, what are the parametric equations gonna be of this one? So to get that 4, what do we need here? 2 cosine t. And it doesn't really matter which one's sine, which one's cosine. We usually, I don't know why, just if it's tradition or what, cosine usually we make with x, but doesn't have to be. It's just gonna change the direction you go around the ellipse, I believe. And so this one's gonna be, oh, wait, not true, hold on. Don't do that yet. We wanna make this 1 first. That's gonna change things. Okay, now we're ready. Okay, because now what it's gonna be is x is gonna be 3 cosine t, and y is going to be 6 sine t. There we go. Okay. All right. I better hurry up and talk about dot product. We're going to go in parallel vectors. All right, so this is 12.4. Talking about parallel and perpendicular vectors. And in particular, we're going to find out there's actually 2 different kinds of products with vectors. So we're going to get a dot product, and a little bit later we're going to cross product. Who knew? Kind of crazy. So geometrically, two vectors are parallel if the lines that contain them are parallel. If the lines that contain them are parallel. Algebraically, what this means, this kind of bothers you, used to bother me, I've come to accept it. Algebraically, V1, vector 1, is parallel to vector 2 if V1 is some multiple of V2, which somehow doesn't seem quite right, but it's going to be that way, so might as well accept it. So we know that, the idea is if this is V1 and we know it's parallel to V2, they have to, like we did, the lines that contain them have to be parallel, so they have to be tilted the same way. But remember, these vectors are slidable. So that means you can take that vector V2 and you can move it over there, right? So there's our vector V2 when we slide it right on top of V1. And now you can see that they're multiples of each other, right? That if you multiply V2 by the right number, it's going to be V1 equal, that V2 is K times V1 for the right choice. Or, pick a fraction, V2 is some multiple of V1, something times V1. Does that make sense? So, I mean, it's a little disconcerting because it doesn't quite match what we think from geometry, but we're gonna kind of expand our idea of parallel. Now, what we do know is that two lines that are parallel, so if V1, which we're gonna say is x1 comma y1, is parallel to, so V1 is parallel to V2, and we'll say V2 is going to be x2 comma y2. So those two are parallel, then we know their slopes must be equal to each other. I want to do that parallel still, I want to go to perpendicular. So it scratch that. Let's say V1 is perpendicular to V2. And we know that the slope of V1 is its rise over run. With me? Well, we see the rise over the run, right? Because this is the horizontal component. You know, we're going over x1, up y1. So the slope of that is going to be y1 over x1. Okay? And in a similar fashion, the slope of the second vector is going to be y2 over x2. Actually, yeah, so those are their slopes. Now, if they are perpendicular, then we know these slopes must be negative reciprocals of each other. Okay, well, another way of saying negative reciprocals, if you take 3 times a negative 1/3, it multiplies to be a negative 1. And if you take a negative 4/5 times its negative reciprocal is 5/4, you're going to get negative 1. The only place that doesn't work very well is if you have the slope is 0, then you're going to multiply that by negative 1 over 0. Well, never mind. We'll talk about that differently. But anything else other than the horizontal perpendicular, they're going to multiply to be negative 1. With me? Okay, well, let's see what that looks like. So what we're saying is that if we multiply this y1 over x1 times y2 over x2, that should be negative 1 if we started out with two perpendicular vectors, which is what we're claiming. Is that okay? So let's see, that's going to be, y1, y2. I'm going to multiply the x1, x2 to the other side. So that's going to be y1, y2 is equal to negative x1, x2. You all right to there? Tell me if I'm going too fast. I'm going to add this to the other side. So I'm going to say x1, x2 plus y1, y2 must be 0. This is what we're trying to get to. When V1 is perpendicular to V2, two vectors are perpendicular, this weird thing here, this sum of products is 0. Well, we are going to call this the dot product. Which seems weird, but really it's not too far off what you might want to come up with on your own if you were trying to make up a multiplication between two vectors. Right, so we have, say, vector u is, say, 3, negative 4. And vector v is going to be, say, 2, 5. Be very consistent with my angle brackets. Is that okay? So we say then u dot v. Okay, now you have to be careful, you can't get too crazy with this. Okay, this dot means a dot product, and we're going to use later this to mean a cross product, just like you're going back to elementary school and early junior high to figure out how to show multiplication again. Kind of crazy. Life is a big circle. So what we do is you're going to multiply their x values. So it's going to be 3 times 2, plus you're going to multiply their y values. Negative 4 times 5. That is the dot product. Now, if that equals 0, we know the vectors are perpendicular. And if it doesn't, well, then they aren't. Now, that probably has some significance, but we'll talk about that later. But this is going to be 6 minus 20, negative 14. So the dot product is negative 14. Is that okay?
So they're not perpendicular.
These are not perpendicular. Okay? All right. So, suppose we have V is going to be the vector 3, negative 2, and W is going to be the vector 4, 7, And, that wasn't what I wanted. Find their dot product. As you practice. Okay. So what do we get for a dot product? 12 minus 14 is your -2. Okay, so here now is u, v, and w. Your challenge, can you show that u is perpendicular to v? How do you do that? Can you show that v is parallel to w? How are we going to show that? So to show perpendicular, we go dot product. Is that what you're thinking?
Yep.
I like the way you think. So that's going to be 3 times v times 4 plus -6 times 2. Since it's 0, we've shown it. So if we can show the dot product is 0, we have shown that those two vectors are perpendicular. We're done. Make sense? How do we show that they're parallel? The v is parallel to w. Oh, we could do it that way, but we have a different definition. Remember how we show parallel vectors?
It needs to be a multiple.
One needs to be a multiple of the other. So I'm going to pick the bigger one. So w is going to be some k times v. What's the k going to be is the question. So we can show that w, which is -12, -6, is what times v? So I have a question? Seriously? So just look at the extras. What do you multiply 4 by to get -12? -3. And -3 times 2 is? That's what we, so -3 times 4, 2. Maybe we didn't talk about this. A scalar times a vector, you just multiply the components by that scalar. So -3 times 4, 2 is -12, -6. So we've seen that w is in fact a multiple of v, therefore w and v are parallel. Is that okay? Okay, so, never enough time. So here's I was going to prove this, but we have to take it on tape so you can see the proof on the other video. This is the big one. So the cosine of theta, so if we have angle u and angle v, so there's u and there is v, they form an angle in between them, right? We're looking at the acute angle that they form. Then it turns out that the cosine of theta is u divided with v over the magnitude of u times the magnitude of v. How cool is that? That comes from the law of cosines. We can show it, but not in 2 minutes. Okay? So we're going to use it. Let's see. To the nearest degree. To the nearest degree. Let's find cosine theta, where theta is the angle in between u and v. If u is the vector 1, 2, and v V is the vector, looks like negative 3, 1 maybe. Oh, is that one? I don't think that's right. Hold on. I'm gonna read my own writing. This is sad. No, that is right. 1, 2, and negative 3, 1. I'm not that. Okay, you ready for this? So we say cosine of theta is, we're gonna take u down to the v. What's that gonna be? 1 times negative 3 plus 2 times 1. So that's gonna be a negative 1. Is that okay? Over, now we need magnitude u. So remember, magnitude of u is gonna be Pythagorean. So that's gonna be square root of 5. And magnitude of v is going to be, and square root of 5 times square root of 10 is 50. We can simplify it, it doesn't really matter because that's the cosine of theta. So if we want that angle, we're going to have to put our calculator in degree mode and take the inverse cosine of negative 1 over square root of 50. I think, if I got that right, it's about 98 degrees. Okay. That's what I wanted to do for today anyway. Talk rushed.